This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
My name is Dick Luthi. I'm a professor at Stanford University. I work in the area of water quality engineering. And with Dave Sedlak, we are the director and co-directors of a large National Science Foundation center on the theme of reinventing the nation's urban water infrastructure. Just one word about me. I think if you were to scratch below the surface of many Stanford professors, you would find that they bleed blue. In my case, I have 3 degrees from Berkeley. I'm a product of the 60s at Berkeley. And in chemical engineering and College of Chemistry, we call ourselves, from that era, the free radicals. All right. Our first speaker this morning is Peter Glick. Peter is affiliated with the Pacific Institute for Studies in the Development, Environment, and Security. He was the co-founder of the Pacific Institute, which just recently celebrated its 25th year anniversary. The Pacific Institute is a independent, non-governmental organization specializing in field of water, economic, environmental justice, and sustainability. Peter is an expert in the area of water policy and management. He's been recognized by a MacArthur Prize. He's also been, which is very prestigious, he's also been recognized by election to the National Academy of Sciences. Most recently, in 2012, he published the book, A 21st Century U.S. Water Policy. And with that, Peter, welcome.
Good morning, everyone. I guess you sort of have to start with your Berkeley credentials or something here. I'm an ergie, woohoo, ergies. If you don't know what an ergie is, you should. I'm not going to describe it. I've known Dick for many years. Dick and I were on the Water Science and Technology Board at the National Academy, and I'm on the Science Advisory Board of the Renew It project at Stanford and Berkeley as well. I'm going to talk about this: why focus on supply is not a solution to our water problems. So that's my conclusion. I mean, I'm not saying you can go to the next session now, but that's my conclusion. It doesn't say supply isn't an answer. It says why a focus on traditional supply options isn't going to solve our water problems. And I have a lot to say. I'm going to go through it pretty quickly to just give you a sense of what I mean. I'm going to talk about what I mean by supply. I'm going to talk about the concept of peak water, which is a concept we've been working on at the Pacific Institute here in Oakland. And then I'm going to talk about some alternatives to that viewpoint of a supply-focused answer to our water. And I'm going to focus on California, but I would argue that much of what I have to say, not everything, but much of what I have to say is relevant for much of the rest of the world as well. So, supply. In the 20th century, water supply meant more water. Build another aqueduct to move water from where we have it to where we want it. Drill another groundwater well to tap an aquifer. Build another dam to store water that we get in wet seasons so we can use it in dry seasons. Supply, that's what we, and I have an engineering degree. I was trained in hydrology and climatology. That was the way we were taught to think about water, and that's brought enormous benefits to us, that focus on supply. California wouldn't look like California today if we hadn't invested in these kinds of infrastructures that move water from the north to the south and store water in the wet season for use in the dry season and so on. And I'll come back to some of that. But that's what traditional supply meant. Let me talk about the concept of peak water before I come back to this idea of supply. And let me do it in the context of curves that all of us are familiar with. Exponential curves that you all know are frankly behind many of the problems that we face today. Global population, described by an exponential curve. This is the population curve for the last 1,000 years, from 1000 to 2000 AD, showing exponential growth in population. Carbon dioxide in the atmosphere over the last 1,000 years. And we heard some talk quite a bit about climate in the first session this morning. Atmospheric concentration of CO2 in the atmosphere over the last 1,000 years. Exponential growth behind many of the problems that we face today. Exponential growth followed by a peak in something followed by a decline. Again, we saw lots of curves this morning, and you see in lots of the sciences that you deal with this kind of graph as well. We see it with US oil production, and the concept of peak oil is this curve. And this is a graph actually of peak oil production in the United States. Oil production in the US peaked in the 1970s, actually in 1970, I think, and has declined since then. And there's a debate about when the world is going to reach peak oil. Peak oil doesn't mean we're going to run out of oil. It's going to mean it's going to become more difficult to find or more expensive to produce, and alternatives will become cheaper and production will decline. But an exponential growth in something, a peak and then a decline, follows this classic shape. Atlantic cod. Again, this is, you can't read the numbers, but 1950 to 2010, cod production, exponential growth in the taking of cod in the Atlantic, followed by, in this case, a collapse in the cod population and a decline in cod capture, and even to this day, the cod population in the Atlantic hasn't recovered. So demands on resources, peaking in resources, and a collapse or a decline in something follows this kind of curve. And the third curve is a classic logistics curve, exponential growth in something, a leveling off, and then a sustained something. We see this in technology all the time, market penetration. This is market penetration over the last 100 years of landline telephones. Somebody invents something, telephones, cell phones, DVDs, all sorts of technology follows this curve. People love them, they buy them, and then everybody's got one. And you're not going to buy, maybe you'll buy two of them, but there's a leveling off of the market penetration, typically around 100%. Or ecosystem carrying capacities follow this kind of curve. Or, back to water, this is cumulative dam capacity, storage of volume of water stored behind dams in the United States. I'll show you a bigger picture of this a little bit later for California, but we learned how to build big dams from a technical point of view. The money was spent to expand storage capacity behind reservoirs in the United States in the 40s and 50s and 60s and 70s when the big dams in the United States were built, and then a leveling off for a variety of reasons, and I'll come back to those in a moment. Another comment about peak water, and this is all in the context of some work I've done with a colleague of mine, Meena Palaniappan, on the concept of peak water. Water is a renewable resource, mostly. A renewable resource is typically defined as a resource that is flow limited. A non-renewable resource like oil is typically defined as a resource that's stock limited. The difference being that non-renewable resources, or the amount you can use, is limited by the amount that's there, the stock. Once it's gone, it's gone. It's non-renewable. Renewable resources are limited by flow. The amount that you use has no effect on the amount you get next year. Think about a river, natural flows, the hydrologic cycle. Doesn't matter if you take water out of the river this year. It doesn't affect how much water you get next year. There's natural variability and so on, but you can't take more than is provided. You can't take more than the natural flow. So renewable resources are flow limited. Water, interestingly, is mostly renewable, but it has some non-renewable characteristics. And in this concept of peak water, that's relevant, and I'll talk about that in a second. So peak renewable water sort of looks like this. You start to take water out of a river, your demand grows because your demand for industrial water use or agricultural water use grows, and then you take it all, and you can't have any more. Once you take the entire renewable flow of a river, you're constrained, and that's peak renewable water. And we see this on the Colorado River. We see this on lots of rivers. And it begs the question, of course, should we take it all? That's an ecosystem question, it's a societal question, it's a cultural question. There are lots of issues associated with that. But that's the concept of peak renewable water. And in more and more of our resources, our traditional response to demand for supply, find more water, is running into constraints. This is the flow of the Colorado River measured at what's called the southern boundary station, which is basically at the mouth of the delta in Mexico. And what it shows is, first of all, lots of natural variability. We have wet years and we have dry years. What it also shows is that in the 30s and 40s and 50s and 60s, the amount of water reaching the delta started to decline. And that's because we built the big reservoirs on the Colorado River and we started to take a lot of water out for our cities and our agricultural demands on the Colorado. And what it also shows now is that in average years, or in typical years, no water reaches the Colorado River Delta anymore. We take it all. We, the 7 states and Mexico. In really wet years, sometimes if the reservoirs are full and then you get a wet year, some flow reaches the Delta. But mostly, we've reached peak demand and peak supply on the Colorado River. And this is true on the Yellow River and the Nile and the lots of ecosystems around the world. Peak non-renewable water looks like this. You take water out of an aquifer, you take more and more, and then the groundwater levels drop, it becomes more expensive to pump, and you run into a peak and you start to reduce withdrawals because it's more expensive. Land goes out of production, like in the Ogallala aquifer, and you start to get a decline. And that's peak non-renewable water. And a lot of our water worldwide now, a lot of our use worldwide is not peak renewable water, but it's peak non-renewable water. And that's another topic for another conversation. And then there's the concept of peak ecological water, which I won't discuss much, except simply to say that it's the idea that we reach a point where the next gallon of water or cubic meter of water that you withdraw from a system causes more ecological and economic harm than provides benefit. So benefits, growing benefits with the more water you use, amount of water appropriated by humans, until all of a sudden the next unit of water you take has negative economic or ecological, or preferably a combination of ecological and economic value. We're good at measuring economic value, we're crappy at measuring ecological value, but that's a question for ecological economics. And that's the concept of peak ecological water, and we argue lots of systems around the world are way past the point of peak ecological water, where we're now causing more harm than we get benefit out of the water we're taking out of those systems. So quick overview on that. So peak water doesn't mean we're going to run out of water. Water is a renewable system, mostly. Where it's non-renewable, we are going to run into stock constraints, and there are limits on what we're going to be able to do in the future. And we are running up against flow limits in renewable systems that are a combination of natural flow constraints and increasingly economic, and I would also argue ecological constraints. And we're hitting peak ecological water in lots of our systems. So what does this mean for traditional supply? California. This is a spaghetti diagram. Lots of you have maybe seen it before. The different colors are the different kinds of infrastructure we have. One of the colors is our federal system. One of the colors is our state-built system. One of the colors are local systems. I'm not even going to look to see which are which. But we've built a lot of traditional supply that's permitted enormous cities in coastal areas far from our sources of water. And that traditional infrastructure has brought enormous benefits to us and some unexpected costs. Part of the problem is this picture. This is withdrawals from the delta, the amount of water we withdraw from the delta from 1956 through last year. And it's the Central Valley Project in blue and the state water withdrawals in red and other delta within delta withdrawals in green. There's a lot going on in this picture, and how you think about this picture depends on your perception. So, some people look at this graph and they go, oh my God, look at this. There are periods of times when our withdrawals from the delta plummet, and not everybody gets to use as much water as we would like. And some agricultural users are low water rights users, and they lose water during droughts. These are droughts, basically. The most recent drought, the 87-92 drought, the 76-77 drought. When there's not enough water, not everybody gets all the water they want. Oh, that's a real problem. Somebody else looks at this graph and goes, well, it sort of looks like we're taking more and more water out of the delta all the time on average. And maybe that's a problem. Maybe we're taking too much water out of the delta. Some people look at this and anyway, there are lots of ways of looking at this, but this is part of the Rashomon picture of our water situation. I'm arguing that the traditional approaches, the dams, the aqueducts, the groundwater withdrawals, are not going to solve our water problems in the future, that we have to think about something different. This is a picture of dam. These are GIS map dam, all the dams in California. There are thousands of them. Okay, maybe we could squeeze in a few more on some of the rivers in between existing dams, which are some of the proposals, or off-stream dams, or raise existing dams. There are lots of proposals out there. But I'm gonna, it's an opinion, I'm gonna state that I don't think that would solve our water problems. This is a blow-up of that logistics curve I showed you for the nation, for reservoir storage. This is California. Total cumulative capacity, water stored behind California dams over time. And you can see we started to build big dams in the 20s, 30s, 40s, 50s. Here we built Shasta, big increment to storage behind dams. And Trinity Dam and Exchequer and Oroville, the keystone of the state water project. This is the federal water project, and so on. And then it sort of leveled off. Because, why? Well, we built on all the good dam sites, and some not so good dam sites, one might argue. Federal money and state money for new projects dried up. We started to realize the ecological damage, the peak ecological issues associated with building big on-stream storage. And there was growing environmental movements, David Brower among them, who raised awareness about the ecological costs, not the economic benefits, but the ecological costs of this infrastructure. Lots of reasons. But the bottom line is that, okay, and up here I've plotted the most likely new additions to storage that have been proposed. Raising Shasta a couple of feet or more, building Sites Reservoir, which is an off-stream storage in the North Delta, squeezing one more dam on the San Joaquin in between two existing dams. Those are the three new big storage options that have been proposed. I don't know if any of them will be built. If all of them are built, we get this additional increment. And I don't think there's going to be much beyond that. We're not going to make this curve exponential again, even if we wanted to. That's not going to happen. That's one of the reasons why I think new traditional supply is not necessarily the answer. We're overpumping groundwater. This is a map, a little hard to read, but basically shows those areas where non-renewable groundwater withdrawals are occurring, especially the lower San Joaquin, where we overpump statewide on average 1 million or 1.5 million acre feet of water a year. That's not sustainable. Groundwater levels are dropping, streams are drying up, ecosystems are suffering. We can do that for a little while longer, but it's unsustainable. It's got to stop. And where are we going to find another 1.5 million acre feet just to replace that overdraft? Much less are we going to expand supply with more groundwater pumping? I would argue no. Climate change, I'm not going to talk about this much. You heard a lot about it earlier, but climate change is going to screw up our existing hydrologic cycle in ways that you heard about this morning. We've done a lot of work on that at the Pacific Institute. We're not adequately planning for those changes in the hydrologic cycle that we're now confident will occur, especially changes in the timing of snowfall and snowmelt runoff on our rivers. So if traditional supply isn't going to work, what do we do? And this is solutions. I think there are other things that we can do. First of all, I'm not saying new supply isn't a good idea. I'm saying traditional supply isn't going to solve our problem. But there are lots of new ways of thinking about supply. Conjunctive use. Recharge some of those groundwater aquifers treat them like reservoirs, fill them up in wet years. You don't lose water to evaporation, and pump them more in dry years. That's conjunctive use, and there are interesting experiments going on already in California in that area. Treated wastewater. There's 1 million acre feet probably of treated wastewater, treated to different standards that we collect, treat, and throw away. That's a new source of supply. It's an asset, not a liability. Innovative water transfers among different users, desalination when we can deal adequately with the environmental and economic challenges of desalination is a potential source of new supply for certain areas. Rainwater harvesting, there are lots of new things we can do that don't require building new dams and aqueducts and overpumping groundwater and so on. So supply, but not traditional supply. I think more important is demand. Let's do more. The short version here is let's do more with the water we're already using. That's a question of productivity, conservation, efficiency, and so on. Dick, how am I doing on time?
Doing all right. We should wrap up pretty quick, though, to leave time for the other two speakers and questions.
We have to rethink management. Our traditional 20th century systems are not going to work for a 21st century California. And there are lots of options there, which perhaps we can talk about later. But a couple of quick comments about, I've talked about new sources of supply. I want to leave you with the demand, some thoughts about demand. This is related to supply, but when you have a leaky bucket and the stuff you're putting in at the top is scarce and expensive, increasingly expensive, I would argue the first thing you do is you plug the leaks. And that's the argument for efficiency and conservation. And it's not brown lawns and shorter showers. We do those things in an emergency. Mayor Villaraigosa talked about the restrictions on outdoor landscape watering. Okay, we do those things in an emergency. But what we're talking about is not lawns, but efficient landscapes, native landscapes. We're talking about efficient appliances and toilets and shower heads and washing machines that do the things we want to do with less water. That's productivity, not deprivation. In 1980, 100% of the toilets in California were 6-gallon per flush toilets, because that's the technology that we had. And then California passed, before the national government passed, efficiency standards, and we started implementing 3.5-gallon per flush toilets, and then 1.6-gallon per flush toilets, ULFTs. And by the year 2003, the Pacific Institute estimated, all right, this is the distribution of toilets. We still had a bunch of old, inefficient toilets, and these were no longer the most efficient toilets, but increasingly we were putting in place ULFTs. New construction, you had to put in an efficient toilet, and so on. By 2020, it might look like this. Most of our toilets will be 1.6-gallon per flush toilets. We'll still have a reservoir, if you will, of inefficient, really inefficient toilets. And now there are new, maybe the colors shouldn't have been the same here, but new high efficiency toilets that aren't 1.6 gallons per flush, but 1.2 gallons per flush. So technology changes, penetration rates change, and so on. There's enormous potential for tapping into wasteful uses of water. All right, so let me give you some final thoughts. Our assumptions that the past is a good guide to the future are no longer valid. The 21st century is not going to look like the 20th century. Climate change, population dynamics, the economic systems we have in place, and sources of financing, the past isn't a perfect guide to the future. Traditional supply options are extraordinarily limited now, here and increasingly around the world, and are not going to solve our problems. There are strategies, though, for reducing our vulnerability to peak water limits and to climate change, and they include innovative sources of supply and a focus on demand and new management techniques and strategies. But we're going to have to think differently, and we're not thinking differently. Water policy in the state of California, even today, is mired in the old thinking. The new California water plan that was just released this week takes steps in the right direction, but in my opinion, they're too slow. And we're going to have to do things differently and more quickly if we're going to prevent the problems that I think we see are coming. Thank you very much.
All right, thank you, Peter. Our next speaker is David Sedlak, who's the co-director of the Berkeley Water Center and a professor in the Department of Civil and Environmental Engineering here at Berkeley. He's a Mazeloff professor in mineral engineering, and his research interests are related to the fate of wastewater-derived contaminants, particularly those contaminants that we find in pharmaceuticals and in consumer products of all sorts. His specialty is understanding the fate of those chemicals as we think about groundwater recharge and water reuse. And Dave will continue the discussion, a little bit of history, but also looking at some of the solutions that are in place today that can serve as a roadmap to the future. Thank you.
Thank you, Dick. Thanks for the introduction. We wanted to remind you that if you have questions in this session, that there should be note cards out there. Write down your questions on the note cards, pass them to the side, or just throw them up at us as paper airplanes, and we'll be good. So when we organized this session, they needed someone to interview Lisa Jackson. I ended up with the job. And then they needed someone to follow Peter Glick. Here I am again. So I have a hard job ahead of me, but Peter did a great job setting up this talk because he told us about how traditional water solutions wouldn't necessarily cut it in the 21st century. And I want to tell you today about some non-traditional solutions. And the way I want to tell you about those non-traditional solutions is to go back a little in history and think about how society has responded in the past to challenges in urban water infrastructure. And I want to show you that what tends to happen with urban water infrastructure is you go through a period of indecision, a period of failing and declining water systems, and a period of argument and debate. But then suddenly ideas come about out of necessity and a revolution occurs. And when those revolutions occur, they're frequently spurred on by university research. And most people don't realize the extent to which university research has played in advancing new approaches for urban water systems. And I think that looking forward in the future and looking forward to solutions, there's an important role for the university to play in the solutions to these kinds of problems. And so what I want to do today is I want to draw out of my research and the research of the researchers at Renew It to show you some of the fourth revolution that's currently going on here in California and the way in which university research is helping to advance it. But let me start by going into the past. And going into the distant past, we think about the first revolution in urban water, which I could call urban water 1.0. This is when people came together in cities, Rome being the best example. The city with close to 1 million people provided close to 100 gallons per capita, which is a huge amount of water considering when this city was built. And it did it with technologies. It was advances in technologies, the aqueducts, which you're probably familiar with, at least looking like this, but really they're just canals underground. But there's an incredible story of siphons and piping and construction materials that made that possible. And along with that revolution in water, there was a revolution in the idea of sewers. So open pits became the cloaca of Rome, and the cloaca of Rome got covered over, and sewers were invented. And that idea of imported water and distribution to household levels and disposal in sewers became the first generation of urban water infrastructure. And when cities started to grow in the second half of the 19th century, and when people started moving to the United States and building big cities, they built upon the Roman experience, and they replicated it. So here you see a map showing New York City's gravity-fed urban water system, where water taken from the Catskills and the Croton watershed deliver water to New York City, and sewers, much like the sewers of ancient Rome, initially discharged the waste to New York Harbor. And then, as Peter showed you with the Colorado River, I think he was showing you the data down here in Mexico where it discharges. The reason that water doesn't necessarily reach all the way down into Mexico is a lot of it's being used for agriculture up here and also to supply water to Southern California. So again, using this idea of imported water as the first revolution. The second revolution in urban water happened when people realized that those sewers that were discharging the water after it was used were becoming the drinking water supply of the downstream community. And the best example of that is the cities of Lowell and Lawrence on the Merrimack River in Massachusetts. These were mill towns, which were among the largest cities in America in their day. And these mill towns disposed their sewage in the old-fashioned way. They put it into the river. Unfortunately for Lawrence, they were downstream of Lowell. And in the 1890s, typhoid fever outbreaks were commonplace. And so Lawrence lacked the ability to find an alternative source of water. And so out of necessity, they started doing serious research in how to solve their water problem and allow them to still consume water that came out of the Merrimack River. And instrumental to solving those problems was the work of the scientists at MIT's Lawrence Experimental Station. So William Sedgwick, shown here in the middle picture, was the sanitary detective that found the sources and tried to stop the worst of the sources coming into the Merrimack. And Alan Hazen, a child prodigy who graduated from Dartmouth at the age of 19 or something like that, was the one who pioneered a lot of the early work in slow sand filters and sand filtration to prevent typhoid fever. And the combination of sand filtration and chlorine disinfection made it possible to drink effluent impacted waters. And in the 20th century, people like Abel Woolman from Johns Hopkins helped transfer this idea all around the world. So the second revolution in urban water, spurred on by university research, made it possible to live in denser and denser cities and for people to consume water that had been contaminated by an upstream wastewater discharge. The third revolution in urban water infrastructure was the construction of sewage treatment plants. And sewage treatment plants were not built to protect the public health of downstream communities. They were built to prevent things like oxygen depletion in waters downstream of sewage discharges and ecological impacts from the organic matter, the nutrients, and everything else that went with the sewage discharge. And the development of sewage treatment can be traced down to the research of Gilbert Fowler, a professor at the University of Manchester, who helped pioneer the idea of activated sludge treatment after visiting the Lawrence Experimental Station and seeing the work on slow sand filters. And here in California, the idea of sewage treatment was pioneered largely here at UC Berkeley. I looked for a picture of Professor Charles Gilman Hyde. I couldn't find one on the web, but I found a picture of the civil engineering building that preceded Davis Hall, and I sure wish we had it back. Any of you have ever been in Davis Hall, because it's a very beautiful building. But Gilman Hyde and his colleagues at Berkeley really did a lot to bring sewage treatment to California. And you can see here in this figure from the EPA, after the Clean Water Act in the 1970s, that revolution that was designed by people like Fowler and Gilman Hyde and many others at the university spread around the world. And so when the Cuyahoga River caught on fire, when people started turning their attention to the environment, the answer was there because university researchers had developed the wherewithal to treat sewage. And so here we are on the dawn of the fourth revolution in urban water supply. And we heard Mayor Villaraigosa tell us this morning about Los Angeles' plan for delivering water. And we heard some talks from Bill and Chris earlier this morning about what our different climate is going to look like, even if we get our act together and stop releasing as much carbon dioxide as we are. We bought into a certain amount of climate change. It's going to mean major investments in urban water infrastructure here in California. And Peter was just telling us we're not going to do it the way we did it in the 20th century. We're going to have to find new ways. This figure shows you the plans that have been put forth for the Los Angeles basin of where the water supply is going to come from in 2035. And you can see what's going to happen is the part of the pie that's imported water is going to shrink, and three areas are going to grow. And those three areas that are going to grow are one called WUE, water use efficiency, the kinds of things that Peter mentioned at the end of his talk. Many of these things are locked in. These changes in plumbing codes, these improvements in irrigation efficiencies, those are locked in and they're going to grow and become an important part of how we solve the problem. But they're not going to be the only part of our solution. And the two I want to talk to you about today are recycled water, which you see here is going to more than double, and capture and reuse. And what we're capturing and using in that case is urban stormwater runoff. So this is the stuff that flows down the middle of the street and goes into the storm drains and flows out to the ocean now. That's going to be our water supply in the future. And this is what Los Angeles' objective is. And you can see the tiny yellow slice there, seawater desalination. It may grow a little bit, but it's not planned to grow to the extent of the other two. And you can ask a question about that later and hear a very opinionated answer from both Peter and myself. Okay. Ask the question, Braden, and you'll find out. So this is and I also wanted to tell you kind of also about some things that aren't captured in that graph, and that's the fact that we're already doing a fair amount of water reuse that goes under the category as groundwater use. So this is the Santa Ana River Basin in Southern California. For those of you who've never been down south, this is Disneyland here. So if you go visit Disneyland here in Anaheim, you'll see the Santa Ana River. And the Santa Ana River is a very interesting place to manage for urban water issues because they only rely on a relatively small amount of imported water. Most of the water comes from the watershed. And one of the challenges for the Santa Ana River watershed is this area up here called the Inland Empire, Riverside, San Bernardino, and that area has grown quite a bit in the last 30 years. So around 1970, it was around 1 million people. It's approaching 4 million people now. And through the growth of those people and the discharge of their sewage, the Santa Ana River has transitioned from what was more or less a conventional California river with ephemeral flow draining the mountain snowmelt to being a wastewater effluent-dominated river during much of the year. And that's interesting because that wastewater effluent-dominated river is the drinking water supply of Anaheim and lots of other places downstream. And what's really interesting about that is the way the Orange County Water District has actually engineered the Santa Ana River to improve water quality as that wastewater effluent is being delivered to the drinking water supply. Here's one feature here, the Anaheim Lakes. So the water flows down the river, and right here, the city has bought some former sand quarries, and they route the water out of the concrete channel of the river basin into the sand quarries, and that's where it percolates into the ground. And that managed aquifer recharge or soil aquifer treatment helps improve the water quality. It's like the slow sand filters that Alfred Hazen had pioneered back at the Lawrence Experimental Station, but in a natural system. But the one that's more important and interesting to me are the Prado wetlands. These are wetlands that built up behind the Prado Dam when it was built as a flood control structure. And as the nitrate levels in the Santa Ana River increased, the Orange County Water District, working with Professor Alex Horn here at UC Berkeley, engineered that system with constructed wetlands to remove nitrate, because wetlands are really good at denitrification. And they use that to knock down the nitrate concentrations to a level that would make it safe to drink. Now, we've been interested in removing some other kinds of chemicals. We've been interested in pharmaceuticals and personal care products. We've been interested in chlorine disinfection byproducts and other chemicals. And so we've been working with the town of Discovery Bay up near the Delta, building a new kind of treatment wetland. It's a shallow open water wetland. There's a poster outside that talks a little about this wetland system. And this wetland is able to remove nitrate like the existing system, but it also is very good at removing trace organic contaminants like pharmaceuticals and steroid hormones and disinfection byproducts. And we convinced the Orange County Water District, because we have a long-standing partnership with them, to actually build this out in the Prado wetlands. And so that little cell here I'll show you in a blow-up, that's what it looks like earlier this summer. The water is about to go in there any week now. I think they're just getting some final touches ready. And just to give you an idea, oops, I didn't realize this does. That's a backloader there. That's a full truck and a backhoe loader. So this is a huge system that they're making a significant fraction of the Santa Ana River's Prado wetlands into this open water photocell in order to remove trace organics, and working with us in a partnership. So in the Santa Ana River, the other interesting place, and the one that people most think about when they think about Orange County Water District and the Santa Ana River, is the facility called Water Factory 21, which was a seawater intrusion boundary. So what happened here was that in the 50s, the groundwater wells here in Orange County were overpumped, and the seawater started moving inland, obeying the laws of physics and moving downhill. And the water became saltier and saltier. And to prevent that salty water from getting into the drinking water wells, the Orange County Water District said we have to inject fresh water to push it back to the sea. Initially, they thought they would do it by desalinating seawater, but that turned out to be too expensive. So instead, they desalinated wastewater effluent. And so starting in the 1970s, wastewater effluent from the Orange County Sanitation District's treatment plant was treated by reverse osmosis and activated carbon and injected into this line of wells here to push the intruding salt water back. And I got involved in research with them in the mid-1990s when they were considering expanding this system, tripling its size, and extending the importance of this recycled water project upstream, when they discovered this contaminant, NDMA, N-nitrosodimethylamine. This is a potent carcinogen. And when the state looked at all the health data for it, they said that any concentration above about 10 nanograms per liter or parts per trillion would be unacceptable to human health. And so we worked with the Orange County Water District to find ways to reduce the production of this compound. It was actually formed during the disinfection process, and it also had industrial sources. And we worked on treating it with ultraviolet light. It turns out that this compound's really interesting because it can go through reverse osmosis membranes. You can see here it's only removed by about 50% during the reverse osmosis process, and then it's destroyed by UV light. So that made it safe, and the Orange County Water District went along with their plans to triple the size of Water Factory 21 and to rename it the Groundwater Replenishment System, and to admit that this was a system for replenishing drinking water and not just keeping seawater at bay. And so this is what it looks like today, and they pump water up to those Anaheim lakes that I showed you earlier, and they inject it, and that becomes the potable water supply. So we still work with the Orange County Water District because they're on the forefront of this revolution in urban water supply, and we're asking questions about what happens when you drink water that used to be wastewater effluent and just came out, it's toilet to tap, let's admit it, came out of a treatment plant, went through reverse osmosis, went through UV peroxide. And so one project that we started initially in Singapore at the Public Utilities Board and have continued with the Orange County Water District has been to identify contaminants in sewage that can make it through the reverse osmosis system into the finished tap water. And the one that turned out to be particularly risky from the perspective of public acceptance of the water were taste and odor compounds. So these chemicals here, pyrrolidone, trichloranisole, and hydroxyvanillin, these are chemicals that have a very low odor and taste threshold. And people can smell them and taste them in their water, and if they have a new water supply and it tastes funny, they're going to reject it. And so this was really hard work. Here's my student, Ava August, here, using the best detector for odorous compounds, the human nose. So you use gas chromatography, and you sniff with your nose, and you find these compounds, and then you use mass spectrometry to identify them. And we found which compounds are present, giving the smell to the wastewater, and we found ways to destroy them. And so now we have ways that we can actually do this kind of toilet-to-tap project and create water that's not only safe with respect to public health, but also doesn't taste funny. And that's good because the train that's left the station in Southern California for so-called indirect potable reuse is moving to the idea of direct potable reuse. So there's a lot of discussion now among utilities in Southern California of no longer putting that wastewater effluent into an aquifer, but piping it directly into the inlet of a drinking water treatment plant. And there are a lot of economic reasons, there are not a lot of logistical reasons that utilities that don't have a wonderful sandy aquifer like Orange County are pursuing this approach. And we could talk about those during the question session. Finally, I want to touch on this last topic of urban runoff as a water supply. So this stuff that runs down the streets, you look at it, you say, would I really want to stick my cup in there and start drinking this drainage water? Well, that is a great water resource because it doesn't have a lot of salt in it. And it causes all kinds of problems like beach closures and damages to streams. And so the Los Angeles Department of Water and Power has an ambitious plan to increase the amount of rainwater that they capture and infiltrate into a reservoir, into the ground. But unlike Seattle or Philadelphia or other places that have the luxury of many, many small storms distributed over the entire year, in Southern California, when it rains, it pours. And so what you have to do is you have to capture that rainwater and hold it somewhere and then inject it into the ground. And so this project, the Rory M. Shaw Wetland Park in Burbank, California, is a project that's been funded by LA Department of Water and Power. Construction slated to start in 2015. And it's a former rock quarry which is dug out, and this is going to capture the rainwater that normally goes into the storm sewers. And then it's going to feed it through this above-ground wetland system. And then underneath this ball field is a percolation basin where that stormwater is going to percolate back into the drinking water aquifer. And when I saw this, I said, that's a really cool idea, but I'm not sure I want to drink the runoff coming off the streets just after it's been through a wetland and percolated through some rocks. And then I went to a field trip to go see this place. And this is the stuff, this is what it looks like in the part of the picture you can't see. That is auto repair lots, industrial facilities, and all kinds of things that you would expect could contaminate groundwater. Surface water. And so we've been working on research trying to identify what kinds of contaminants you might worry about, things like herbicides, things like products that come off of the tires of cars, things that like this one here. If anyone, you put, I guess it's that flea medication you put on your dog as like on their back. I should ask Bill Collins if he uses this on his dogs. It's got this crazy molecule here with these carbon fluorine bonds and everything like this, and it can be detected in urban runoff. And so we wonder about these things making it into the water supply. And rather than just throwing up our hands and giving up on this potentially useful water supply, we're starting research on ways to destroy these contaminants. And so rather than just percolating this stuff through the soil, we're looking at engineered geomedia. That is, rather than just using sand, using things like activated carbon and biochar to absorb contaminants, using things like iron oxides and manganese oxides to chemically degrade these contaminants, and hopefully, coupled with the wetland system, finding a passive treatment system to purify this water as it's undergoing the recharge process. So, some final thoughts about this issue of fourth generation of urban water systems. What is Water 4.1 going to look like? If this is the way we're getting to 2025 or 2035, how are we getting to 2050 and 2080 under these new climate scenarios? So inevitably, there's going to be more potable reuse, like what you saw in Orange County. More stormwater harvesting, like what we're starting to see in Southern California, and certainly more water use efficiency, and in ways that we probably can't even anticipate based upon what's on the market now. But I think there are other things that we're going to see and other research opportunities. For example, there are a number of aquifers in Southern California that are too polluted to drink from because they're near former hazardous waste sites. I think if we can treat those, we have a great source of water. There are off-the-grid housing developments that people have proposed and explored in Europe. It's possible to actually do much better work with making water use efficiency by recycling water within the home. There's gray water, there's roof water, you name it. There are all these options out there that are still too expensive because the technological research hasn't been done yet. And then finally, at the bottom of the list is seawater desalination. It's certainly the way that Australia went in response to their major decade-long drought. It's the way that Israel's going. It's the way that Spain is going. I think if we can figure out how to do seawater desalination well, it will be another part of California's water portfolio. So with that, I just want to end with some acknowledgments. I can't read out the names of everyone here, but I wanted to emphasize that the work done in Renew It is a collaboration between Berkeley, Stanford, Colorado School of Mines, and the Swiss Federal Institute in Zurich. And also here at Berkeley, it's not just engineers who do this. It's people in the College of Environmental Design, like Bill Eisenstein and Louise Mazinga, and Mike Kaparsky in the Wheeler Center for Law. So I realize that this is an interdisciplinary project. I talk mostly about the technological part today, but there's a broader social science and institutional side. And lastly, I want to acknowledge the funding agencies and the utilities that have helped us. And if you want to learn more about the fourth generation of urban water, a book that I wrote is coming out in January, and you can find the website there. So thank you very much.
All right, David, thank you very much. Our next speaker is Dave Sundig. Briefly, he's going to tell us how we're going to pay for all that, or not. Dave is a professor of agricultural and resource economics at Berkeley. He's the Thomas Graff Chair of Natural Resource Economics. He's the founding director of the Berkeley Water Center, and his research concerns environmental and resource economics, regulation and technological challenges, applied economics, risk, and public finances. Prior to his position at Berkeley, Dave Sundig served as a senior economist on President Clinton's Council of Economic Advisors. And Dave Sundig is one who I've learned so much about in terms of overcoming barriers to finance and paying for some of the thoughts and strategies that we've heard about today. So, Dave, have at it.
Well, thank you very much. It's nice to be here with all of you, many familiar faces, some new ones. One of the things that's fun for me about working on water is that it's a classic interdisciplinary problem. the challenges that we've heard about today, they can't be solved solely by engineering. They can't be solved solely by biology or legal analysis or economics or any other individual field. It's a classic interdisciplinary problem. So what I'd like to talk about today is the economic aspects of some of the themes that David was talking about and Peter talked about previously. And part of the way I would phrase this is, what are the economic pluses and minuses if you put yourself in the shoes of an urban water manager and you've got this whole potential range of water supply and conservation investments that you can be making and ultimately asking your ratepayers to pay for? What are the economic factors that would determine whether or not you would want to adopt one strategy versus another? And in doing that, I'll touch on a number of themes that have come up already. I'll probably talk about them in slightly different terms. But I do, just as a threshold comment, I want to come back to something that Peter was talking about, and I think very rightly, when he started talking about how we've reached an age of limits in the development of traditional supply projects. That's definitely true. I'll talk a bit about California. I think it's true in many other places around the world too. But in a way, one thing I want to bring out here is that the situation is even worse than that comment implies, because traditional water supply projects are performing worse and worse. And that's for a number of reasons, and they're projected to perform even worse in the future than they do at present. And that has to be factored in, again, when you put yourself in a very practical position of being an urban water manager who's trying to decide, how am I going to meet future demands for water? So that's another very important theme I'd like to talk about today. So one factor that urban water managers look at, and I think they need to look at even more than they have in the past, is this notion of reliability. And reliability means different things in different contexts, but what I mean here is the ability of a water supply source to meet a particular level of demand. So if that supply source is subject to intermittent outages, whether due to seismic events or droughts or environmental regulations, that supply source would be considered to be less than perfectly reliable. And that's certainly the case with many of our most important pieces of water infrastructure here in California. There are two major kinds of stresses that are being felt on traditional surface water supplies in the state. First is environmental regulations. And this is a combination of local regulations, but most importantly, federal regulations, especially the Endangered Species Act. This is being felt on the Colorado system, certainly in the Delta, and I'll talk about the Delta a little bit more in a second. But environmental regulations are increasingly chipping away at the performance of these traditional systems that import surface water into urban areas. And second, of course, climate change. Some effects arguably are being felt currently. Certainly the expectation is that climate change will have a deteriorating effect on reliability off into the future. So that's one source of stress. The traditional sources of supply are not performing as well as they used to. Second, and here, I think there's room for some technical debate, but focusing attention, like I'm going to do in the talk, mostly on Southern California, our work projects that there actually will be some continued demand growth. Not at anything like the rates that we experienced in the 60s and 70s when the state was growing so much. But there will be some modest increase in water demand growth out to 2050. And there are factors that work in both directions. I would argue that on balance, there's a slight positive tilt to this whole thing. On the increasing demand side of the ledger, there's projected to be more people. Southern California, Northern California, it's a popular state. And the growth is projected to occur primarily in inland areas and not in the coastal areas that are already largely built out. That has important implications for water demand in a couple of ways. First of all, inland areas are hotter. that leads to more water demand. Inland areas also have lower land prices, so people tend to have more outdoor irrigation. They have larger lot sizes, more outdoor irrigation. So the fact that growth occurs inland as opposed to in coastal areas tends to increase water demand. Income levels are also projected to increase. One absolute empirical regularity that's been established in hundreds of papers is that as income goes up, people purchase more water. So as income is projected to increase, that has an increasing effect on water demand in California. But there are factors that argue for a decrease in demand. Rates are going up. Water's a commodity just like many other things that we purchase in a marketplace. As the price of it goes up, people use less of it. So that's one factor that definitely will increase demand going forward. And there's also public policies to encourage conservation that are being adopted in California, so that'll tend to decrease demand. Taking all of this on balance, what our econometric work suggests is out to 2050, there would be something between now and then, in aggregate, like a 20% increase in water demand between 2012 and 2050. So that amounts to something much less than 0.5% per year, way below the historical rates, above where they've been the last 10 years, but way below the historical rate of demand increase. So those would be two factors that I would point at right away as being stresses on urban water systems in California. Now, this is very important. This goes to the point about environmental regulations, but also climate change. And just a little bit of teeing up, this is an exceedance curve, so it's essentially a probability distribution. And it tells you the percent of years that deliveries on the state water project system, which takes water from the Delta down to Southern California, exceed a certain level. So when the curve goes up, that means more water. But this curve also tells you how the supplies are distributed between wet and dry years. And so the red line, that's where the state water project is right now. And remember, the state water project accounts for about 1/4 of all the supplies going into Southern California. So it's an extremely important supply source. What DWR is projecting is through primarily increasing environmental regulations, but also some effects of climate change. So this goes out just to 2050. If we went further beyond, it would look more dramatic. But looking just out to 2050, this is the kind of deterioration that they're expecting in their own project. And what you can see is that this amounts to roughly a 30% reduction in the mean, due again mainly to ESA regulations, but also some shift of water between wet and dry years. So not only is the mean going down, but the reliability of the water supply is going down, and that more water tends to come in wet years. Now that's got major implications for the management of these urban water utilities in Southern California that have grown up relying on the state project as a foundational system. So what are the responses? I promised David no inside baseball, but I have to say one thing that's California specific, one response to that graph is the Bay Delta Conservation Plan, which I've been working on a lot over the last couple of years. The state and federal contractors that take water out of the Delta, they're contemplating spending $25 billion to prevent that curve from shifting down, right? $25 billion is not going to provide any new water. That's just about keeping things in place. Now, that's its own economic decision, whether or not that's the right way to spend money, or whether or not there are other ways that money could be spent that would be better for ratepayers ultimately. But again, just understand the magnitude of the problem. You have state and federal contractors in ag and urban areas that say they're willing to spend $25 billion just to prevent this from occurring. So, what are some responses to these stresses? First, I think there's more incentive to expand the water supply portfolio through investment in alternatives. And this is maybe another way of saying what you've been hearing about this morning from David and Peter. It's more of a economic take on it, but I think we're all sort of arriving at the same place. And these alternatives could include recycling, desalination, stormwater capture, on and on. Now, when it comes down to the nitty-gritty economic comparison of, say, a water utility manager wanting to invest more heavily in a traditional supply source or invest in an alternative supply like recycling, there are a couple of things that have to be compared. Very often it's the case that the alternative water source has a higher unit cost, and I'll go through some numbers in a minute. But the alternative water supply might also have a different reliability profile. Desalination is not really subject to fluctuations in precipitation. It's going to be there every year, and that's valuable. Recycling is also valuable for the same reasons. Anything that enhances groundwater storage is valuable for the same reason. It all improves reliability. So to do a full and accurate comparison of the costs of a traditional supply source, like taking water out of the delta, to an investment in an alternative water supply, there has to be a comparison made that includes the value of reliability. So that's what I want to talk about here. And when you include the value of reliability, these things become much closer than they might otherwise appear. So just to give you an example, if you go back to the Orange County area that David Sedlak was talking about, I do a lot of work with the Municipal Water District of Orange County, which is affiliated with Orange County Water District, but MODOC, the Municipal Water District, they're in charge of the imported water supplies that are coming from the Delta and the Colorado into Orange County. And the cost of water on that system, just to give you some examples here, the untreated Tier 1 kind of base rate that has to be paid for that water currently is $593 an acre foot. If it's treated, it goes up to $847. And then the Tier 2 rate, which is sort of on demand, there's no long-term commitment for it, that's much more expensive. That's in the range of $743 an acre foot to right around $1,000 an acre foot. So that's what imported water costs if you're, say, Orange County Water District ultimately. But neither of these supplies is totally reliable. So we're going to get to the reliability in a second, but suppose I were Orange County or Ventura or San Diego and I wanted to look at an alternative water supply. What would that cost? Well, these numbers are much higher. And these numbers are higher than you might have seen before because people sometimes forget that past investments in water supply alternatives have been heavily subsidized through a whole variety of state programs primarily. But if you take the subsidies out and look at the actual cost, this is what emerges. And as an economist, who works in planning a lot, that's appropriate to do because there's no guarantee that these subsidy programs are going to continue into the future. And furthermore, when something's subsidized, that means somebody else has to pay for part of it. And if we're looking at welfare on a statewide point of view, you wouldn't want to include that anyway. So here, just a few examples. The groundwater replenishment system, the very one that David was talking about a minute ago, has an estimated cost of right around $1,000 an acre foot. Even though parts of that system, are not new, the costs are still around $1,000. The Inland Empire Utilities Agency project, which is in the upper part of the watershed that David referred to, their recycling project had a cost of right around $1,500 an acre foot. Central Basin, which is still in Southern California, but more on the LA side, their water reliability project had a cost of just under $1,700 an acre foot. And the Elsinore Valley project was right around $1,300. So these projects, and I should say I didn't include everything in here, the San Francisco East Side Recycling Project has a projected cost of $4,500 an acre foot. So the costs are all over the place, but if you compare to, again, put yourself in the shoes of an urban water manager in Southern California. You can buy water from a traditional source, or you could do this. This is more expensive. Just based on, a 30-second analysis, these numbers are higher. Well, what about desalination? That's even worse. Ocean desalination, let's make a distinction between ocean desalination and brackish groundwater desalination. Probably the best data point for ocean desalination is the recent project in northern San Diego County, the Carlsbad project. No one knows exactly how that's going to come out, but the projected costs are between $2,000 an acre foot and $2,300 an acre foot. Peter says it's higher. It could very well be, yeah. The brackish water desalination is cheaper for a whole number of reasons. That's more down in the range of $1,200 to $1,700, but you get the basic point. Actual costs for a particular project, they're all over the place depending on how much pipe has to be laid and what are the characteristics of the system, what's the characteristics of the source water, all sorts of things. But these numbers are quite a bit higher than the cost of imported water. So if we were going to do an actual side-by-side comparison of costs, this is part of the story. But there's more to it than that. I'm not going to get into questions of quality here or environmental benefits, and that's obviously a very important part. But I do want to talk about this notion of reliability, because what I see a lot from urban water managers in California is that they're focused on not being able to meet levels of demand in every year, and that's an important part of their planning. Well, I would lose my license to practice economics if I didn't show some kind of a graph like this that had some curves crossing, so bear with me for just 1 minute. What is the cost of unreliability? So what is the cost of, Peter showed the picture of the lawns going brown and taking a shower with a bucket, that kind of thing. What is the cost of that, of this mandatory short-term conservation? Well, there are two costs associated with it, really, when you break it down. The line that is sloping down at an angle, that's the demand curve for water, so that's the amount of money that people are willing to pay for different units of consumption. And the dashed line, the lower one, that's the beginning rate. Oh, here, I can actually do this. There. So this is the rate that's charged. This is the demand curve. So this is the amount of water that people would choose to consume. That's the target level of demand that the utility is trying to satisfy. Well, now suppose the utility says, uh-oh, we ran out of water from the delta. We don't have enough to sell you. We've only got this to sell. So what are the economic costs of that? Well, the first cost is that people have to cut back their consumption at the prevailing rate, and so they're willing to pay this amount of money. They actually have to pay this. They get this much less consumption, so if we add up this area under the demand curve above the rate, that's the first type of impact from not having enough water in the short term. So that's what we call in economics a loss in consumer surplus. But that's not the only cost. What usually happens in water utilities are very capital intensive. Most of the costs, say 90% of all the costs that water utilities bear, are fixed costs. And fixed costs don't change with the level of water that's going through their system by definition. So the rate that the utility charges is normally way above the actual marginal cost of putting one more unit of water through the system. So this line down here is marginal cost. And so what that means is that if the utility is selling less water, it's not covering its fixed costs. And if this were an investor-owned utility, the PUC would set up what's called a rate adjustment mechanism, and this amount of money that is no longer going to cover fixed costs, that would be used to raise rates in the future. So that's a second kind of a cost of this mandatory short-term conservation. So as an economist, this is the number, or this is the concept that we'd like to be able to put some numbers on. What is the value of reliability? How big is this shaded area? And what are the likely magnitudes of future disruptions? And what are the probabilities of them? Then, whether it's for Orange County or Ventura or San Diego or East Bay Mud, you can calculate what is the value of reliability. So you look at the reliability profiles of two alternative supplies, calculate a reliability premium, and then you can put these things on an equal basis. So we've actually been working a lot with water utilities throughout California for the last 4 or 5 years to implement this kind of a framework for reliability planning. And I should say, I mean, just to give full credit, this is normal in the electric industry. This kind of reliability planning is absolutely standard. It is not normal in water. At least it wasn't normal 5 years ago. It's becoming more normal. But so we're really extending something that is pretty common in other utility sectors. But to calculate this reliability premium, you need to know some information. You need to know something about that demand curve, how steeply does it slope for different sectors. You need to know the marginal cost of service. You need to know the magnitude and the probabilities of potential future outages. And so I'm not going to go through. I would also, yeah, he's right. I would also lose my license if I didn't have something like that, because we're all about econometrics these days. But let me just show you some numbers that I think will indicate how important reliability is. So we look, just as a thought exercise, across all the water utilities in the Metropolitan Water District service area in Southern California. So this is, you know, a lot of people in Southern California. I think, what is it, 17 or 18 million. And we looked at what would be the cost of a hypothetical mandatory 10% outage across that whole area, 20% and 30%. So this is just a 1-year outage of these percentages. And here are the numbers you get. Ratepayers would be willing to pay something like $235 million to avoid a 10% outage of 1 year in duration. If you increase that to 30%, which we've really never seen in California but might see in the future, that number grows to like $1.6 billion. That's for 1 year in just one part of California. So clearly this is consequential. And if you think about the implications of that change in state project deliveries that I showed you at the beginning, this could happen. Right? This is a logical consequence of that kind of a deterioration in a foundational water supply. Running that through a little bit more and getting to the probabilities, this is what might happen in Southern California if that state water project delivery curve shifts down the way I showed. And this shows you basically percent shortages and then the likelihood of them occurring in any given year. Traditionally, the line in Southern California has been the water supply is almost totally reliable. So this distribution would have been masked at 0. Not the case anymore. And you can see here, even for a shortage, you know, something like 12.5%, which would be very, very large in historical terms. There have certainly been episodes of mandatory conservation where that was required, but they're uncommon, and this would be a big magnitude. That has something like a 15% chance of occurring in any given year, right? So this is a very high, I would argue unacceptably high degree of unreliability unless something gets done. So if we calculate an implicit reliability premium for the year 2020, our thought exercise shows that coming out at between $200 and $400 per acre foot, down at the level of an individual utility. So we're looking at variations in demand. For the year 2035, that number goes to 500 to 1,000. Well, now these get to be really interesting magnitudes. Go back and compare, say, these numbers to these numbers. And if you add, you can do it one of two ways. You can subtract the reliability premium from the cost of the alternatives, or you can add it to the cost of the traditional supplies. If you add $500 to $1,000 to these numbers and compare to these numbers, now it's a much closer call. So if you put them on an equal footing in terms of relative degrees of reliability, if you're a water manager, these alternative investments make a lot more sense. So again, reliability is not the only answer, but it's something that I think is increasingly important and that water managers are conscious of. So to end with a comment that David made, here at a public university like Berkeley, we view this kind of outreach work as being fundamental to what we do. And certainly UC Berkeley researchers have made important contributions, not just in California, but beyond. But we view this as being sort of fundamental to our jobs. I work with a lot of the same agencies David does, probably a lot of the same agencies that Peter works with. But this way of thinking about the economics of adoption of different kinds of water supply alternatives, I think is getting traction. And we'll see where it all leads, but it is at a minimum very interesting. All right, thank you.
Now, this is a question for Dave Sedlak, and it has to do with pharmaceutical compounds and pollution prevention. And how can we, what would be the role of utilities in keeping pharmaceuticals from getting into the water supply?
So if you look around at the response that water utilities have taken to the issue of pharmaceuticals in the environment, it's been driven mainly by a concern about the potential impacts on aquatic ecosystems and not drinking water. But they have initiated pharmaceutical take-back programs and unused medications coming it back. But the best estimates on the effect of that is that it has a relatively small impact. And so taking back unused medications is not really going to decrease the loading of pharmaceuticals to a treatment plant. In parts of Europe, they've thought about more of what they call a green pharmacy approach, of actually decisions made about which drugs are given to patients being based upon the persistence of those compounds in the environment. And there's some pharmaceuticals that have structures that lead them to make it through a treatment plant, and there are others that are biodegradable. And so the decisions, and this comes back to the larger question of all of the chemicals that we use in the environment. When the sewer is the drinking water supply, you treat it differently. You treat it like a watershed. You think about product selection. You think not only about pharmaceuticals, but you think about consumer care products, and you think about industry, because a significant percentage of a lot of the water coming into a sewer is coming from commercial and industrial sectors. And the source control programs in that sector haven't really seen a close reexamination since the 1970s. And so with this new paradigm of where we're going to get our water from, it's not just pharmaceuticals, it's all chemicals that we use and put down the drain.
Okay, thank you. This is a question for Dave Sedlak and for Peter. Where do you see the role of waterless toilets and urine separating toilets, things that are used in Europe, but what about their role in California and the western U.S.?
Well, let me answer that more generally. I hinted at this with the slide I showed about toilets and the distribution of toilets over time. There is enormous potential for doing what we want to do with less water by changing technology alone. We could talk about changing behavior, changing practices, as well as a component of that. And I think we haven't fully tapped into either the existing technology that's out there or potentially new technologies that will come along and let us do the things that we want to do. And I had a slide that I didn't show for agriculture. This is really sort of the city's urban discussion. Agriculture is obviously a huge component of this that we haven't talked about. But, and this is something I wanted to actually say to David Sunding, I think this focus on reliability and the economic value of reliability is really great. It's really important. San Diego has decided to build the Carlsbad, or to pay for, not to build, but to pay for the Carlsbad desalination plant. The cost of that plant is, per acre foot of water produced, is huge. Part of that is a reliability value. Part of it is in what I like to call, and I hate the Metropolitan Water District, fee that San Diego is willing to pay to stop buying water from the Metropolitan Water District. I mean, there are lots of things that go into their willingness to pay for that. That's another story. But at $2,500 an acre foot or $2,000 an acre foot, and I'm not sure that David's analysis fully addresses this, but we can talk about that. You can cut the demand for water through conservation and efficiency investments. And there's a reliability value to that as well that I don't think is fully appreciated. So you can enhance supply through the different options that David pointed up, but you can cut demand as well. And one of the wedges that this David showed was a conservation and efficiency wedge. And he showed it sort of as a supply option, but it's a demand reduction option. It depends on how you define it. And there's a value to that as well. And I think we need to integrate that into our planning, because if you don't have to use an acre foot of water, you don't have to provide it. And if we can cut withdrawals from the Delta, because you don't need the water in Southern California, that has a value, an ecological value, an economic value as well. And I don't think we fully calculated that value.
I wanted to get back to the waterless toilet because I think it's worth answering that part of the question as well. The real potential in the vacuum toilet or the waterless toilet is not the additional savings of water, but the potential of taking a house off the grid and allowing more efficient conversion of solid waste into biogas. And so if you can do that, you suddenly have a household where the toilets are no longer attached to the sewage system, and the solid wastes are used to make biogas, which can then be used to make electricity. And then that opens you up to urine separation and resource recovery. Both of those ideas are still a lot more expensive than any of the technologies we talked about today. So maybe that's 4.1 or 4.2. And hopefully we'll develop it to a point where it becomes much more attractive.
And a question for Dave Sunding. Can you explain a little bit more about the alternative conveyance system, that $20 billion investment, and what the role of that is, or why we should do it or not do it in the context of the sorts of things you were talking about for Southern California?
Sure. So without going totally into a BDCP discussion, I think the primary motivation for the new conveyance is to add another point of diversion that gives those who are operating the system, the state and federal systems, more flexibility about where they're taking water out of the Delta and when. So it basically gives them another degree of freedom to manage the whole system. From the perspective of Southern California, what it does, because it provides ways to comply with regulations that aren't possible right now, what it does is it increases water supplies. It maintains them at roughly the current levels. So again, the $25 billion of investment, and that's not all for the new conveyance. It's mostly for the new conveyance, but it's also habitat and some measures to address what they call other stressors on the system. What that $25 billion does is basically keeps supplies in place. It doesn't provide a lot of new water, or really any new water. It just keeps things from deteriorating into the future.
All right. Just one other question for you.
And I should just as an add-on, because we're talking about this theme of, essentially an urban water supply portfolio. Estimates differ, but even if the BDCP were to occur, it's not accurate to say that the Delta fix is sort of in place of investment in alternatives. even those who are advocating for the BDCP recognize that there will have to be a huge amount of investment in alternatives in California just to make ends meet 50 years into the future. And by alternatives, I would include conservation in that. So the BDCP is not the answer to all the problems in the urban water system in California. There would still have to be a development of, I think, something like 1.5 million acre feet of these alternative water supplies and conservation programs out to 2050.
And that would make up for our shortfalls at the moment.
Yeah.
One other question for you, that the economic models tend to assume that people will be richer in the future, but climate change implies we'll be significantly poorer. So why do we stick with these models?
Right. Yeah, that's in California. I haven't seen any climate change models that have people getting poorer. That's certainly the case in other parts of the world. Maybe Peter can correct me if I'm wrong, but all the models that we've been using show that household income, or the projections are that household income would be increasing in California off into the future. And I should say, we're only going out to 2050. We're not going to 2200 or anything way out into the future, just to 2050.
One last question, since we have lunch coming up here. And the question, I guess David Sudlak was addressed to you, but you all can comment. Do you drink bottled water, and is it good?
I only drink bottled water under duress. If I'm going to drink anything in a bottle, it usually has carbonation of one kind or another. Oh, absolutely.
Well, that was the first part. I abbreviated.
Oh, absolutely. I drink tap water here, or tap water in Berkeley is wonderful, and some of the best I've ever had. And I drink tap water in Southern California, and Dick has even seen me drink out of the groundwater replenishment project. So I guess I'm an adventurous drinker.
A shameless plug here. I wrote a book about bottled water a couple of years ago called Bottled and Sold, the story behind our obsession with bottled water. This country has an incredibly great tap water system. Really great. A system that most of the rest of the world wishes they had. It could be better. There are new contaminants. We don't fully understand the health implications of those contaminants. But it's a great system, and we ought to invest more in it. You know, we talk about $1,000 an acre foot water, $2,000 an acre foot water. When you drink tap water, it's $1 million an acre foot, or $2 million an acre foot or more.
Bottled water.
Bottled water. It's 1,000 times more expensive than tap water. And we could get into the issues about regulation, who regulates it, how often is it self-monitored. I mean, there are a lot of issues there. But I'm a tap water fan, so.
Well, let's thank our panel for a wonderful discussion.